Welcome everyone to our weekly entertainment. We just had an excellent ITC colloquium by Elena D'Onghia, who is visiting us on sabbatical. Where is Elena?
I'm here.
Oh, okay, she's over there, and we will hear from her soon. We'll start with Jenny Bergner, from here. And she will tell us about the survey of complex cyanides in protoplanetary disks. Looks like the projector is not on, Mark. The projector is not on. And that will be followed by Elena D'Onghia, who will tell us, she's visiting, as I mentioned, on sabbatical from Madison, Wisconsin, and she will tell us about satellites within satellites, the luminosity function of the Large Magellanic Cloud in the Gaia era, meaning that we are observing them in the Gaia era. Obviously, they existed long before. And then we'll hear from our colloquium speaker today, the CFA colloquium speaker, Dimitar Sasselov, who will tell us about exoplanet ocean worlds. How salty. He visited my office this morning and asked for if I have a salt container. Apparently he plans to demonstrate something. And then finally we'll hear from David Sobral from Lancaster. And he will tell us about re-ionisation is salt. Lava naphtha emitters are all we need. Okay, we look forward to hearing that. Jenny.
So thank you guys. As a little bit of background before we get started, we know that comets and planets form in protoplanetary disks. So the content of gas and solids in the disk is going to set what chemistry can occur on forming planets. This means that if you want to make things that look like the organic biomolecules that we have here on Earth, you need to inherit the precursors for this chemistry from the disk. We can learn something from the prebiotic chemistry community that's studying how the origins of life arose here on Earth. And it turns out that this group of molecules called nitriles is really key to origins of life chemistry. So for the non-chemists in the room, a nitrile is a molecule that has a carbon-nitrogen triple bond in it. And again, in terms of driving the chemistry that leads to things like RNA, lipid, and protein precursors, these nitriles seem to play a really important role. We can also look at solar system comets, which preserve material from when our solar system was forming. And we see these nitrile-bearing molecules like HCN, methyl cyanide, and cyanoacetylene. And we see that they're both common and relatively abundant in solar system comets, which still fits with this picture that potentially this class of molecules was important for the origins of life on Earth. So the question that we'd like to answer more broadly is, how does the content of nitriles in other disks where solar systems are assembling compare to the content within our own solar system? In a disk, we have different carriers of the nitrile group, so CN, HCN, methyl cyanide, cyanoacetylene, and each of these can be inherited to some extent from the protostar. We can also sort of shuffle the cyanide group between these different carriers in the disk through an active chemistry. So one key aim is to understand how nitriles are inherited as well as reprocessed in disks. And another way of asking this question is to say, how is this nitrile group partitioned among its different carriers in the disk? So we've been able to observe nitriles in disks for a couple of decades. In the early days, we could only take unresolved spectra detecting simple nitriles like HCN and CN in disks. As telescopes got more advanced, we could start to resolve the emission spatially of simple molecules and make detections of more complex species, but we were not able to resolve them spatially. And then really since ALMA in the last couple of years, we've been able to actually resolve where the emission is coming from for these more complex nitrile species. So this is Karin Oberg's paper from just a couple years ago. And until very recently, there's only a single disk where these molecules had been detected. So we're really sort of at the cutting edge of being able to characterize the emission of these complex nitriles in disks. So we set out to follow this up and understand more about this chemistry. So we're using ALMA band 6 to target methyl cyanide and cyanoacetylene. We targeted 6 different disks that span about an order of magnitude in their age, their mass, and their luminosity. So we have 4 Titari disks, which are sort of similar to our sun, and 2 Hervig AE disks, which are a little bit bigger and more luminous. So jumping straight into our detections, we see that methyl cyanide is firmly detected in 3 of the 6 disks. We have 2 tentative detections also, depending how generous you're feeling, if you want to call that real or not. We also detect cyanoacetylene towards 5 of the 6 disks. So we're seeing already in this sort of first sample of these molecules in disks that they seem to be quite common. In some of the disks, we detected multiple rotational transitions, which lets us build what's called a rotational diagram and pull out the excitation temperature and column density. So when we do this, we derive temperatures between about 30 and 70 Kelvin. And the nice thing about disks is they have a very sort of characteristic temperature structure because you have the hot central star irradiating your disk, and you end up blocking more and more of the light as you go deeper into the disk. So based on a temperature of 30 to 70 Kelvin, we can sort of map this emission back to this warm molecular layer in the disk. And unfortunately, this is not actually probing the material that's going into planets and comets directly because this is happening deeper down in the disk. So for 2 of the disks in our sample, we had really bright emission. So we were actually able to model the emission and derive radial abundance profiles. So we take a physical model of the disk, accounting for the temperature and density profiles. We couple it with a parametric abundance profile, and then we try to reproduce the emission that we observe. So our model looks like our observations, so we're happy. And these are the abundance profiles that we pull out. So we see that in the inner 100 AU or so of the disk, we have abundances of about 1 to 10% for methyl cyanide with respect to HCN. And for cyanoacetylene, it's between 1 and up to 100% with respect to HCN. So this is telling us that these complex nitriles seem to be abundant at these comet and planet-forming radii in disks, and they're also important carriers of the CN bond. So if you're trying to understand sort of the global picture of how nitriles are inherited in disks, you can't ignore these more complex carriers. So in the disks where we didn't have enough signal to noise to do the radial profiles, we can still extract disk average abundances. So on the top is showing the methyl cyanide to HCN ratio, and on the bottom is the cyanoacetylene to HCN ratio for the 5 disks where we have detections. And the first thing we notice is that we have really remarkably consistent abundances across our disk sample. So despite the sort of order of magnitude variability in the physical properties of the disk, we really don't see much sensitivity in the actual abundances of these molecules. We're also interested in comparing to comets to see how similar our solar system is to these disks. And again, we see really quite remarkably consistent abundances. The caveat, of course, is that our nitrile observations aren't directly probing this region where planet and comet formation are happening. So there's a little bit of difficulty in interpreting what this actually means for the sort of material that's going into planets and other disks. But the fact that we see such similar abundances across this wide range of physical properties seems to be telling us that this chemistry is robust. And it doesn't really care much about the physical properties of where it's occurring, whether it's the properties of the disks themselves or comparing the disks to the comets. So an important next step from here is actually using these constraints on the complex cyanide emission to benchmark our models of how chemistry works in disks. So this shaded region here is showing what we expect from a generic model of disk chemistry run a couple years back, and the lines are showing what we derive from our observations. And so we see that the model's not really doing especially well. And so now that we have these observations, we really need to benchmark these models. And this is important because these are some of the biggest molecules that we actually can detect in disks. And so if we want to have any sort of insight into what the complex chemistry in disks is doing, we really need to tether our models to the molecules that we actually can see to be able to predict what's going on that we can't observe. We're also working on observations of HCN, the main carrier of the nitrile group, in a survey of 14 different disks, trying to get better constraints on what this main carrier of the nitrile group is doing in disks. And yeah, with that, I'll just summarize. So we're really entering an era where we can begin to characterize the emission of complex nitriles in disks. We see that they're very commonly detected and that they seem to be important carriers of this nitrile group at radii where planets and comets are forming. It seems to be a robust chemistry, so it doesn't care much about the physical properties, which may be good news if you're trying to generate lots of nitriles where planets are forming. And we're looking forward to more work benchmarking models and more observations. So, thanks. Yes.
Much more complex molecules associated with it. So, what do you foresee as next steps in perhaps seeing more complex molecules that could be organic chemistry?
Yeah, so I think this is an interesting question because it's not clear that bigger molecules are going to survive delivery to planet surfaces. So whether we can detect bigger and bigger molecules in disks and their precursors, I think we need better constraints on what that actually means for what's delivered to the surface. So again, the reason that we're interested in these complex nitriles and simple nitriles is because they're carriers of the nitrile group. So that's really the piece that we need to be delivered intact to the planet, but whether these are the particular molecules that survive in the end, I think we still don't understand.
So you noted that your observations don't quite probe the disk heights where the comets and planets form. What do you think would be needed to actually probe those regions?
Yeah, so these were pretty high energy transitions, so they're kind of more, you only expect to see emission of these transitions in warmer material. So we can get lower energy transitions with ALMA, but we need a lot of time to do it. So if they decide someday to give us like 20 hours to stare at disks and probe deeper, then we would love to do that. Otherwise, James Webb would be great, again, for getting into the composition of the midplane. But with ALMA, we're sort of going to be limited in how deep we can probe.
Must depend on the radial distance from the star. So in other words, is that velocity information from the line shape, so you might know from where the emission takes place in this.
Yes, it depends. Our resolution isn't great here, so I don't know.
Talking about spectral resolution.
Oh, yeah. But the spatial resolution isn't great, so I don't know how close to sort of the planet-forming region we can get.
Yeah. I was actually quite surprised to see that in all these disks you find robust chemistry, because you would expect that different UV radiations, pollen densities would really affect the abundances very much. So would you say that the disks are quite similar by chance, or is it just like some chemical, you can get some chemical insight that indeed the chemistry does not depend on all the parameters?
Yeah, so I think we still don't know exactly why it's so similar. It was surprising to us as well. We were kind of hoping to see some trends with the physical properties of the disk. I guess my guess would be the abundances that we show are with respect to HCN. So I think it's maybe an internally consistent nitrile chemistry. where if you sort of normalize out how much HCN you have, then everything looks similar. But the absolute amounts might be quite dependent on the disk properties.
And the models also tell you a similar story?
I don't know in detail what the models say on that.
Any other questions? Well, I'm actually finishing 1 minute earlier.
Oh.
Like unusual.
I just use this one, right? I guess. Okay. Thank you. Okay, so I'm going to tell you about something different than what I presented at the colloquium. So the Large Magellanic Cloud and the Small Magellanic Cloud, so before 2016, were considered to be a pair. However, and at the point that many theorists and in many papers, there was always quoted that the SNC, the LMC might have come as a pairs, but definitely there are no other associated galaxies. However, after 2016, things changed, and so this is a view of the Large Magellanic Cloud, the Small Magellanic Cloud in the Magellanic Stream reference. So this is actually the Magellanic Stream. I have to say that here there are among the best experts, and they've been the best experts about the Magellanic Stream. So, the pair now, in 2016, on the projection on the sky, 9 new dwarf galaxies have been discovered as ultra-faint dwarfs, and they are, located more or less in the same region of the sky as the Magellanic Clouds along the stream. So this, after 2016, people start thinking again about that maybe the clouds, came with a cohort of dwarfs. And indeed, with the advent of Gaia, year to date after 25th of April, people have looked immediately, the stars, because you have parallaxes now, proper motions, which stars of the dwarfs and which dwarfs could be associated with the Large Magellanic Cloud. So I'm quoting here an interesting paper from Nitya Kalivajoli. She was a graduate student at Harvard, and she really did an excellent work on this. So here is, this is actually a prediction from a simulation with Armater only for the, for eventually mapping the stream of the Magellanic Stream. And these are all the dwarfs that we know in the galactic coordinates here, that we know on the sky. So these are the classical dwarf, like Draco, Ursa Minor, Carina, but also the new ultra-faint dwarfs discovered in the last few years. And now, what they did in this paper using the new Gaia DR2 data is actually using the proper motion to see which of these ultra-faint dwarfs are actually associated with similar proper motion than the Magellanic Clouds. And Carina 2, Carina 3, Heidi 1, Horizon 1, they are all, these 4 dwarfs seems to be, seems to qualify to be a cohort of the Large Magellanic Clouds. So, okay, they also look at in other properties, for example, the angular momentum. If you compute the angular momentum, because you can get the 3D velocity from the Gaia DR2 data, and again, they look at only the ultra-faint dwarfs, but they still see that maybe 6 of them do qualify in terms of angular momentum. So 6 of them, these red points here, might have within the error bars, might be in agreement of having similar angular momentum of the clouds, so they might have come actually with the clouds. So what is now the work I'm presenting you about? So this is work leading from my student, Stephen Pardee, is about the classical dwarfs. So I want to go back to Donald Lindenbell and his amazing inspirational idea. Yes. So in the 70s, it's coming from him. It's really coming from his report. Some bad weather during an otherwise successful photometric observing run gave me time to ponder the Magellanic Stream and to wonder whether, like the Magellanic Clouds, other near neighbors of our galaxies were associated with streams of neutral hydrogen, the Magellanic Stream. So talking, basically he identified eventually Draco, Ursa Minor, and probably Sculpture being aligned with the Magellanic Stream, and maybe even Fornax. So of course, even 10 years ago, when I came here at the beginning, I had a paper coming up with George Lake where we postulated that the Magellanic Clouds were coming into the Milky Way as a group of dwarfs, and so we came with the idea, basically, that that dwarfs. So the Magellanic Clouds, they are satellites of the Milky Way, but they can host other satellites, which are actually other cohort of galaxies in the lambda CDM models. So what we did here is now searching for which of the classical dwarf could be associated with the Large Magellanic Cloud and the Small Magellanic Cloud. And the idea is that because in the lambda CDM models, the distribution of the mass functions, the mass function of satellites, is actually self-similar. This is for the dark halos. Of course, the luminosity function is not necessarily self-similar. At a certain point, some of the dwarfs will not form stars; they will be completely dark. However, the idea is to check in the lambda CDM how many of the bright dwarfs we would expect in the Large Magellanic Cloud if this is, the host of a group of dwarfs. So we used here the Auriga simulations, which are sets of 40 simulations with hydrodynamics in the cosmological context. They are from the group of Volker Springer, and they are Milky Way-sized galaxies. So we found many of the galaxies that some of the galaxies seem qualified to be like a Large Magellanic Cloud and having a cohort of dwarfs. Now, what we are expecting in the lambda CDM? So if the Large Magellanic Cloud is actually quite massive, as some of evidence would suggest it might be, so it's around 10 to the 11 solar masses, we are expecting between 3 and 5 classical dwarfs. And when I say classical dwarfs, I'm not talking about the ultra-faint dwarfs, because also in these simulations we cannot resolve them. Okay, so something like Ursa Minor, or Draco, or Fornax. So in the luminosity function, those would be the dwarf that are at the bright end of the luminosity function of the LMC, but they're not the LMC or the SMC. So are the next one in the luminosity function before we go to the ultra-faint dwarf. And then if the Large Magellanic Cloud is actually massive enough, between 3 and 5 would qualify, should be part actually of the Large Magellanic Cloud, even if the clouds are at the first pericentric passage, which is always the case when the clouds are very massive. If they are lower mass, so let's say 5 times 10 to the 10, then none of the dwarfs would be actually part of the Magellanic system. So the LMC would have come actually even alone, or eventually only with the SMC. So given this prediction, we went back to the Gaia DR2 data, and we look at now, so for some of the dwarfs, the Gaia DR2 has a different proper motion than the ground-based telescopes data from the past, especially for Carina. And also a little bit for Fornax, the proper motion changed in their measurements. And this now turns out that if you look at the angular momentum, so if you make an analysis of the angular momentum of the classical dwarfs with respect to the Large Magellanic Cloud, we see that we identify that Draco, well, basically Carina and Fornax are the ones that are, even in terms of distances, maybe the closest to the clouds, but also Draco and Ursa Minor have a similar proper motion. So in terms, similar angular momentum. So using the data, these 4 dwarf galaxies cannot be excluded in being associations with the Large Magellanic Clouds. The way that people haven't considered so far the data is actually integrating the orbits given a potential. So I'm not doing that. So because we don't really know what is the mass of the Milky Way. So if you don't make assumptions, I would say that maybe Draco and Ursa Minor are a little bit too far from the clouds for being the first pericentric passage associations of. But Carina is actually very close. to the clouds in terms of angular momentum, and fornax would also qualify. So going back to Lindenbell, I think he might have been right, and he was probably right, and right. So I think I stop here because I forgot what is my conclusions. Yeah, sorry. I had conclusions. Here they are. So the take-home message is definitely the Gaia DR2 data are confirming that at least between 4 and 6 ultra-faint dwarfs are part as associations of the clouds. They might have come as a cohort of the clouds. However, if they would have come just without the bright dwarfs, then there's a luminosity function with the big gap at the bright end. So there must be some of the classical dwarfs that qualify to be part of the Large Magellanic group. And so this is also what the lambda CDM would predict in hydrodynamical simulations. And I think the data are not inconsistent in qualifying at least Carina and Fornax as part of the Magellanic group at the first pericentric passage. I stop here. Thank you. Yes, this is an excellent point. I think people are trying to look for now if which of the globular clusters might be associated to that, and which dwarfs might have brought globular clusters. Definitely, Fornax has associated, I think, 6 globular clusters, and I don't know exactly the location with respect to the stream, but this is, of course, a point that has been taken because it has to be considered. So if they come in groups, some of the globular clusters came with the dwarf as part of them, and now, also if it's the first pericentric passage, they might not be too dispersed. Thank you very much.
Any surfers in the audience? Okay, so behind Avi's back, I have the full inventory of salt in the ITC in my hands now. And you'll see why. Ocean worlds. This is a topic which relates to the fact that in the last 5-10 years, thanks to big surveys like Kepler and small surveys like MERTH, we now know that planets, which we call ocean worlds, are very common. They're not in our solar system, but they are out there, and they're very exotic in many ways. So Amit Levy, who is a postdoctoral fellow here, is the person who, over the last 5-6 years, has become an expert on modeling those. First as a pre-doctoral fellow here, and now as a postdoctoral fellow. And I really want to tell you that he's the person to be giving this talk, and he will tell you at some other opportunity a lot more about these worlds than I'm going to talk about today. So I'm just going to stay with the saltiness and the pH for today's talk. So what are the ocean worlds really in terms of general conceptual definition? These are planets which are the size of the Earth or larger, for which a very large fraction of the total mass is water. In our solar system, we have satellites of giant planets that have similar composition, But they're so much smaller that geophysically they're also very different because the water mantle in those satellites is in a very different state than in a big planet where the pressures are extremely higher than that. These kind of planets were actually conceived here with then postdoctoral fellow Mark Kushner in 2003, who wrote this kind of out of the blue paper about the possibility for such planets. Alain Leger and the French had actually been thinking about that and wrote about that. And then 10 years ago, we spent a lot of time with Diane Valencia and Riku Kono at the EPS to actually model those worlds in detail. So basically, from a geochemical point of view, you have to realize that there is a big difference between these three types of planets which have water, and even type 2 may to you seem like an ocean world, just like in the Hollywood movie, compared to Earth. Really, from a geochemical point of view, the big difference becomes when you move to type 1, which is a planet in which the liquid water has no longer direct access to the silicate mantle and all the molecules and elements that could be mined from it. So the basic questions are obviously how can we tell observationally, and most of the modeling had to do with atmospheres because that's what we hope to do in the coming years by observationally studying the atmospheres of such planets. So the most important question then is the question about transport of volatiles through this ice mantle. And I keep calling it an ice mantle because this is the technical term for it, but these are the so-called high-pressure hot ices, ice 6, ice 7, ice 10, and so on, which are exotic forms of water which are solid. But what you have to understand also is that in a mantle like this, just like in our silicate mantle on our planet Earth and planets like Mars and Venus, you actually continue to have convective mixing. And convection is alive and well. So this solid ice is actually moving slowly. As you can see, the time scales to the surface of the order of 500,000 years. But on a geological point of view, that's really pretty fast and vigorous. So there is transport. The transport is not what you may find in ice sheets that we know in the solar system, including Pluto and the small satellites or the big satellites of the big planets, because any molecule, or for that matter, ion or anything that is passing through those ice mantles has to be encased in the water molecule matrix. We typically call these clathrates, which means essentially cages. But under those very much higher pressures, even those clathrates have to be given a different name. And a lot of the work which was done here in the last 5 years by Amit Levy was actually understanding the physics and the chemistry of those forms of clathrates which are at high pressure. Because they really then determine what happens in that very thin area right above there where you have the liquid ocean. It may be an ice shield, but the liquid ocean interacting with the solid ices. And so what we know is that molecules like methane and carbon dioxide are efficiently transported to the surface, and you may end up with water worlds have a fairly carbon dioxide-rich atmosphere for that reason. What was not clear, and that is the work that I'm reporting on today, which was just published earlier this year, is what is the state of the liquid ocean itself. And we're interested in the liquid ocean itself because these planets of interest to us are mostly in the habitable zones of exoplanets and other stars. So in other words, we expect to have a liquid ocean in contact with the atmosphere. That's the definition of the habitable zone anyway. And so then the question becomes, what is the state of that ocean with respect to the atmosphere and the observational signatures that we may hope to see. So the first thing to do is to understand what is the salinity, the concentration of ions in a liquid ocean. because this is the only way then you can go to the thing which we are really after, which is to find out what is the pH of that water ocean. So it's a necessary step. So when we did that necessary step, we somewhat surprisingly realized that actually there is a new desalination pump that would act in an ocean like this, in the mantle and the ocean, not the ocean so much, but more in the water mantle. And the reason for that is because brine is always less dense than rock. So on the Earth, that never happens, that you may have the rock, even molten rock, interact in an unusual way or in an inverted way with respect to salty water. But when the bottom of the liquid ocean is also water, which happens to be one of those ices, ice 6 and ice 7, although they're always denser than pure liquid water, in some cases, and recent experiments have confirmed that, some of those forms of ice, particularly ice 6, becomes actually less dense than the briny liquid water itself, and you will get an inversion. These experiments were done in the past 4 years, and the result of this desalination pump is us using laboratory experiments which people did in France to the case of water worlds, and somewhat surprisingly realizing that there will be a pump. In geophysics and geochemistry, people call a pump a cycle of that sort, driven by convection, in which you will have a symmetry between the downdrafts and the upwelling flow because of salt exclusion level somewhere, and that's due to the fact that there is the sodium chloride, salt crystals here will exsolve and actually will be denser and will go under to the rocky core. So it turns out that these timescales, when you do the calculations, which is not easy and is the major part of this paper, these timescales are 20 to 900 million years, which is again short, and compares to the timescale for this overturn, which is half to 1 million years. And that means that the oceans are not going to be salty. So the next question then becomes, what about the pH? So who can tell me what will happen to the pH of my cup of water here when I put a lot of salt in it? What happens to the pH? Nothing. The answer is nothing. pH is not determined, or the concentration of hydrogen ions is not determined by solving, not sodium chloride into this water. It's determined by chemical reactions. So the saltiness of the ocean determines how you calculate pH, but does not actually change the pH. So we managed to do that and found that these oceans would be extremely acidic, very acidic. And just to put this in perspective, this kind of pH between 2 and 3.5 is available in some places like Yellowstone on the Earth, but nothing lives there under those temperatures and pH balances. Just for fun, this is extremophile data for many microbes of archaea, bacteria, eukaryotes, and you see where we are there is cranberry juice to orange juice. So I'll stick with my oranges. Thank you.
All of this chemistry that you mentioned is without the assumption of life. But what's your expectation? Do you think life, the chemistry of life, exists in such world?
I would say, to answer your question, that this doesn't necessarily mean that these bugs cannot live there. It may mean that this kind of conditions have never, or certainly not now, existed on our own planet. Cold, very acidic water. Hot, very acidic water, yes. This is from our recent field trip in Yellowstone. This is a very acidic pool next to a geyser, but it's 3.7. It's not even as acidic as this, but still, there are bugs living there, a lot of bugs. This is Imperial Geyser in Yellowstone. So basically, the question is not on Earth, but certainly these bugs probably can adapt to that with Darwinian evolution over time. I think there is a bigger problem with life on ocean worlds is simply they're very low concentrations of anything else, including ions. This basically oceans essentially very distilled and acidic, but distilled, and there is not much in them, and so you can't do much chemistry.
And so you would expect that Europa and Enceladus probably have no
No, Europa and Enceladus are not big, so they actually have access to those chemicals. It's just when you become as big as the Earth or bigger that this desalination pump starts working.
questions. Go ahead.
So, does this mechanism work for, like, do the vehicles only work for the sodium chloride, or does it also work for other types of salts?
Okay, so we did do it for sodium chloride, partly because the experiments so far have been done with sodium chloride. There is no expectation from theory that it will be different from calcium or other salts, but this is kind of the future work, is to see how other salts will behave under those conditions, because you need to know the full ionic content of it. But sodium and potassium are the main ones that we expect from an abundance point of view. So if they behave like that, we don't expect a major change in the overall conclusions, even if some other salts are highly represented.
Let's thank Dimitar again.
I have to return that. Thank you.
Great. Well, I guess the title is a bit provocative, and you can blame it on Erica, not me. And mostly what I'm going to talk about is something that is, I think, not so provocative, but more exciting. And it's really, it's more like this. I think it's about to be solved. And I think over the last few years, people have finally started to measure the right things to allow this to be possible. Now, the epoch of reionization is obviously extremely exciting for a lot of reasons. It's when the first sources of light became to be, maybe the first black holes soon followed. And there's a lot of questions that people tried to address. How early it started, what were the sources driving it, how long did it actually last for? And obviously the important thing to drive it is we just need Lyman continuum photons with energies in excess of 13.6, and we need enough of them that actually escape whatever black holes or galaxies. And over the years, people have been now accumulating quite really nice evidence, specifically at kind of the end of reionization, where you can look at the Gunn-Peterson trough with quasars, GRBs. You can do it really well. And then it becomes a bit more complicated once you go into the epoch of reionization, because all these probes saturate very quickly. But there's been a lot of progress in using Lyman alpha emitters as tracers of what's going on, trying to determine what is the neutral fraction, and then trying to compare it with what do we need in terms of galaxies and AGN. And obviously, I think the other evidence that's now quite strong is how patchy reionization is. So that comes from lines of sight studies in quasars, but also even understanding that within the epoch of reionization, there seem to be some very big bubbles already, fully ionized. Now, the standard approach in the community, and specifically more for the observers, so I guess we're all to blame, is to pick this approach. I think the first time that was proposed was by Madao in '99, which is very UV-based. And this is obviously, it's very simple, but there's a problem, which is what we need is not the UV, it's Lyman continuum, which means that you need this extra parameter, psi ion, which essentially translates whatever UV photons you have into Lyman continuum photons, which for a kind of a long time has been completely uncertain, and people just didn't mention that. And also, you only care about the photons that actually escape the sources. So you need to determine the escape fraction. Now, you'd think that when there's kind of three parameters that all matter, that as a community, we would kind of split our efforts in determining the three. But in practice, and I guess because there's only money associated with getting the UV with Hubble, there's been a lot of push into kind of just nailing down the UV luminosity density, and just forgetting about all the other things. And I guess, fortunately, we made a lot of progress. I think, unfortunately, it's somehow probably the reason why the very high redshift community has become a little bit of aggressive. I hope this becomes way better so we can focus on the science and collaborate more, discuss things without insulting each other. I think that would be really nice. But also the important thing is, no matter how well we determine this, because you have the other two terms, if you don't determine them, then it's pointless. I mean, why should we be discussing about small changes in rho UV if we don't know how to translate it into Lyman continuum, or if we don't know what is the fraction that escapes? And using this methodology, and again ignoring our ignorance of F escape and psi ion, just 5 years ago, this was a picture that we thought we were, or the universe we were. And the conclusion was that we really needed the faintest UV galaxies, meaning more Hubble time, and we really needed those galaxies to extend up to the highest redshifts, again, more Hubble time and James Webb. And without doing any actual work and just letting the Planck team do the work for us, in just 2 years, the conclusion dramatically changed. So same observations, the conclusions were now that we actually don't really need the faintest galaxies, and we actually don't need them to really extend up to the highest redshifts, because mostly the Thomson optical depths came down by a lot, which means that with normal star-forming galaxies, again, making those assumptions without actually measuring them, they seem to work. Now, the reason for it is because over time, and I'm not saying that tau is evolving really, but over time, tau in terms of observations has been declining significantly. So maybe if you're very data-driven, or if you run a kind of a machine learning, you'd think that solving re-ionization just means sitting back and let tau go down. And then only a single galaxy will ionize the universe. So this means, of course, that re-ionization happens much later on. It's probably quite quick, and we don't need as many faint galaxies or extreme conditions. So is this solved? I mean, is this all? Can we just take this approach and solve re-ionization? And I think definitely not, because this only works if we make these assumptions, which we have not validated at all. Right? So 20% just came out of nowhere. And specifically because when people looked at actual Lyman break galaxies, which these galaxies are, at redshifts 2 to 3, typically there's like 0 or 1% escape fraction, definitely not 20. And to make it worse, I think there's kind of not only lack of measurements, but also the way we do science, we tend to only publish when we detect, we don't publish when we do not detect, which means it's a big mess. And we don't really understand what's going on for the full UV population. Now, fortunately, and some people are in the room also conducting these measurements, pushing for it, in the last kind of couple of years, people finally started making the measurements that we need, which means measuring the ionization efficiency, psi ion, and also finally finding galaxies that leak Lyman continuum photons. And I think the big conclusion, and that will come to what I'll argue, is that every single one of these galaxies that are leaking Lyman continuum, as far as we can tell, is a very strong Lyman alpha emitter. And at the same time, the galaxies with the higher psi ion, the highest conversion between UV to Lyman continuum, are also Lyman alpha emitters. And I think the thing that really nails it down in terms of the technique, and what I would argue that we need to do, has been Chuck Steidel's paper this year, which really kind of extends the studies that have been done in the local universe to really show that if you know how strong Lyman alpha is, or you measure its equivalent with, you can predict the escape fraction from Lyman continuum. So if you select things in terms of Lyman alpha, you can couple those. And you can really solve the equations without making any assumptions. I mean, purely based on what we can see. So you can put these numbers to the test. So if we use actual observations, kind of thinking of the population as a whole, thinking in terms of the Lyman break galaxies, they represent the full UV population. We now have a measurement of what should be psi ion and what is kind of the typical escape fraction. It's very, very low for the full population. And we can take Lyman alpha emitters. They only represent a fraction of the UV, but they have very high psi ion, and they have relatively high escape fractions. These are measured. They're not 20, but they're about 13%. And if you solve it in this kind of UV framework, you show that Lyman alpha emitters actually can do it relatively easily. And with this very simplistic thing of all Lyman alpha emitters being the same, and they also very easily get to the Planck optical depth. Now, the final minutes of the talk, I'd like to propose something that's perhaps even more interesting, which is to get rid of the UV framework. I mean, what we need is our Lyman continuum photons. There are ways we can trace them more directly with recombination lines, and specifically with Lyman alpha. And there, we've been doing a lot of work to trying to calibrate and understand ways you can predict the number of ionizing photons just based on the observed Lyman alpha and its equivalent widths. So you can get rid of psi ion, and the only thing you need to do is then measure what is the luminosity density of Lyman alpha photons, which we can now do really, really well. And we can couple these things together, and we can use the results from Steidel and from the green peas in the local universe to link the equivalent width distributions that we see for the different redshifts and assign them escape fractions. And if you do this, and these are very preliminary results, but with a Monte Carlo approach, really trying to nail down all the uncertainties, I think we're showing that you can really do this without any wild assumptions, just based on direct measurements from quite a lot of teams that are converging to it. So I think this is really exciting. A lot of work needs to be done, but I think this is the way to progress. And the big question, of course, within this framework is to understand whether we need the full Lyman alpha emitter population, whether we only need the bright ones, the intermediate, and to kind of quantify that, and also put any AGN that exists within the context. So I'll leave you with the conclusions. If you want to discuss this or anything else, I'll still be around until tomorrow, and I'll be more than happy to do that. Thank you.
The escape fraction is obviously angle dependent. If you have a galaxy, then there will be channels along which photons escape and channels where. So it really depends on your viewing angle. And it's a three-dimensional. So there would be a probability distribution of escape fractions. Even in the ideal world, you would have a probability distribution. You can't have a correlation between escape fraction and Lyman alpha emission. There would be some large spread. So can you comment on the spread? Also in Steidel's work, it seems like there is a factor of a few.
Yes, and because I think you can see it both also from the work of Aram with the Izotov's Lyman continuum leakers. I think what the observations are showing us makes sense in the sense that the escaping Lyman alpha emission is a required condition to see Lyman continuum, but it is not, it's necessary, but it doesn't guarantee. So there's going to be a lot of Lyman alpha emitters that may not have any Lyman continuum at all because they can still scatter. They can scatter. There's other channels where Lyman alpha can get to us that Lyman continuum photons cannot. So, and I also agree that the way to do it has to be statistically because of the inclination angle. And obviously, I agree that specifically from a simulation point of view, and so I had this slide just from Nick Bender. It's incredibly hard to even think of solving it kind of numerically, but empirically, it seems like we can at least tie it with the observables that we use. And specifically, the point about using Lyman alpha emitters is that we can use it as a selectable. An equivalent width is something that we can measure very easily, and we can control for in the selection. So at least we can now ask the question whether it's enough and whether we already have the population needed.
So I'm curious about this tau measurement, right? So Planck has got a significantly lower value. Right? WMAP initially had a very high value, but
Yes.
then they changed their mind. Then it's perfectly flat. WMAP 3 on up to 9. And now Planck has got a tiny, tiny error bar and it's distinctly different. So is it understood why there is this disagreement between the two?
Yes, so it's both things. So one is the Planck team claims that the systematics are now handled way better, but it's mostly on foreground removals, as far as I can understand. So the big difference between, and I think the Planck team is now also trying to reanalyze WMAP's
That's the question.
data with their foreground removal and the way they do it to show if this is the
See whether
case.
it's consistent.
Yeah.
Okay.
And is it clear why WMAP was wrong so much in the first place?
I think it was for the foreground. I think there's a lot of foreground that had not been removed, as far as I can
First one, I
understand,
think
which
they
pushed.
did something a little
But
bit,
they
but then they corrected it.
They claim they never made a mistake.
Well,
You can look at this. Yeah.
yeah.
So the mapping between the two liquids, the escape fraction was measured at some redshift, so do you expect that to fall as all redshifts, or is like the properties of galaxies are somehow relevant for that relation?
So it's been measured at the moment, I think in a systematic way by Steidel. So this is redshift 3, but the relation, as far as we can tell, doesn't really change. I mean, it's not the same plot anyway, so you can't see it. But around redshift 0.3, it seems to be the same. So it doesn't seem. The big problem, obviously, is once you go to higher than redshift 3, the intergalactic medium transmission is just too low that to actually measure the escape fraction. Even at redshift 3 is already hard because there's some lines of sight where, I mean, it's basically to get this number right. It's relatively hard. So in a way, redshift 2 is even a bit better because there's less space between you and the galaxy for the intervening medium. Whether this holds at high redshift, we don't know. But I guess if anything, it should only go up. I mean, that's the argument of everyone when they used the 20%, was saying that conditions at high redshift will make escape fractions go up. So if anything, maybe this thing will change, or maybe it will go up in Lyman continuum, but also go up in Lyman alpha, and therefore the relation may stay the same.
Any other questions?
So one of the things that you alluded to is that we're getting really good at measuring the fainter end of the UV, LBG population. And I really like that you're avoiding LBGs and just using the Lyman alpha emitters to try and understand ionization history. But to what extent do you need to know the faint end of the Lyman alpha luminosity function? Do you have a sense of how much the uncertainty in that drives uncertainty in the reionization?
Oh yeah, so the measurements I showed you, so this it already, I mean, you see the uncertainties, they're real. So those are already propagated into the uncertainties you see here.
So do you think if there was a much better measurement of the faint end of the luminosity function, like do you have a sense of what?
I think what's driving it, it's still kind of this is more important at the moment still than the faint end. And it also depends on, I think that's also, it's quite important to understand what are the contributions from the different populations. Because I think the bulk of it is still going to be more kind of towards the bright end, but that needs to be done.
Well, that's consistent with what we see in the local universe, because the star formation efficiency in small galaxies is quite small.
Mhm.
So in fact,
Yeah, they don't count as much once.
does not count as much in terms of star formation.
But I think even the latest Robertson with Planck already showed that actually you do not need to integrate that much. So I don't know why people kept discussing it, at least in the context of reionization, of course. I mean, there's other interests of why you want to see whether it goes down or up, but
What's the alpha of this luminosity?
it's about minus 1.9.
So minus 2 divergence.
Yeah.
What does the faint end does max?
Well, logarithmic. Logarithmic.
It means that you get corrections which are as big as the linear corrections on the left-hand plot.
Yeah, but my point is you don't need to integrate it all anyway. You integrate it numerically only. I mean, in this case, it's only being integrated to where we can see, to 10 to the 41. Well, sure, yeah. I mean, it will have to go down, I think. Yeah.
There is logarithmic divergence as you move decade by decade to get divergence from the contributions at the levels of tens of percent. That's what I'm saying. Which, yeah, but tens of percent may not be too much for you.
Yeah.
Okay, well, let's thank all the speakers.
Such good talk today.
This 50% water plant,
Yeah.
why does it just collect water and nothing else?
Oh, we have, well, first of all, it does collect a lot else. It has ammonia, it has all these molecules that, but the water is the main constituent. And the other molecules become encased in the water, like carbon dioxide, methane, and all the heavy stuff sinks into a core. So in a certain sense, probably the way this works is the planet starts by mostly accumulating rock and heavy material until it grows to about the mass of the Earth, and then it starts accumulating the lighter stuff. And if it never gets too much hydrogen and helium, then the water becomes the major component. So for some or other reason in our solar system, this never happened. But we see this as to be the most abundant type of planet out there.
And you know that just from the density, is it?
Yes,
That's how you
from the
figure it.
density and the sheer numbers. I mean, there's so many of them that even if half of them is hydrogen covered, like Neptune and Uranus, which, by the way, are called ice giants for that reason, because,
Okay.
the difference there, though, is that you never have the opportunity to have a liquid water ocean. So the atmosphere is totally just a hydrogen-helium atmosphere, just like Jupiter. And so the water is an afterthought, which is in the interior. In those cases, the planets are generally smaller anyway than Uranus and Neptune. The hydrogen and helium are gone or never accumulated. And so now you have a completely different geochemistry. That's the difference.
Get rid of the hydrogen. Why? Oh, I see.
Hydrogen, that's okay. Yeah.
Why would you have a CO2 atmosphere? Why wouldn't you see